Dear students, today we are going to discuss about Astable Multivibrator. So in the previous lecture, we have discussed about Monostable Multivibrator and the functional diagram of 555 timer IC. Astable Multivibrator, also known as free running multivibrator, also said as free running oscillator. The reason is it do not require any additional input like a monostable. In monostable, what we learned is this is a circuit you will be having, you will be giving some triggering input, right? This is a triggering. When you give the trigger, you will be getting your higher output. Then it will return back to the stable transient state. Yeah, another thing here important to observe is it will be retained in the same low state until if until it get the next triggering. Once it get the triggering only it will go to the higher state. Otherwise it will retain in the same state itself. That is about a monostable. But in the astable it's something this is a novelty here. The circuit is not stable in the either state. It's continuously switch from one state to another. This is very important thing to listen here. The triggering is not required. No trigger. No triggering in the stable movement. The circuit is not stable in either in any state, right? So it will switch continuously from one state to another state. So one of the noticed application is a relaxation oscillator. So with this basic principle, so we can get the many like a solution to the real-time problems. So this is a very novel idea. It can be used in the many real-time problems. Okay, when you look at the what is the main difference in this slide, I will say what is the major difference that we will see in the stable. The first observation is your timing resistor. Right, in the monostable, the timing resistor are RC, but here the R was splitted into RA and RB. The reason behind everything will be seen in the working principle, right? When you see the charging path, this is your charging path through the VCC. So the charging path, this is a charging, right? This is a charging, the capacitor. So the path will be RA plus RB into C. So that is a very important to notice. The discharging path will be RB into C. RB into C. So that is another thing to be observed. So discharge is here RB into C. See, another very important here is the 6th pin and the 7th pin both are shorted, but in the monostable, in the 2nd pin you are giving the triggering input, right? But here 6th pin and 2nd pin both are shorted, and we know that the 6th pin is your threshold and 2nd pin is your triggering input. It's both are shorted and connected to this capacitor. Okay, now let me explain about this terminals and how it was connected. So we know that 8th pin is your supply and the 4th pin is your reset. Both are shorted and connected via VCC, and 3rd pin is output, right? So it is connected via one power amplifier. Then here the 7th pin is a discharge. It is connected between RA and RB, discharge, okay. And 6th pin, very important, threshold pin and your triggering pin both are shorted and connected this simple RC network. And 5th pin is your control voltage. It is connected to the ground via capacitor. The reason, you know, to avoid the ripples, unwanted noise from the ripples from the DC voltage. So that is the reason why you are connecting the capacitor in between the 5th terminal towards the ground. So this is a connection point of view, I said the difference also. We will come to the working principle after practicing the circuit. Okay, so now I'll teach you how to draw the circuit. Very simple way. First, we will create a divider network. The 5K divider network is the first resistor. So you can put a 3 resistor continuously. Right. Okay. So this is your ground. So you can make it more precise. Okay. Positive supply. Now I'll be connecting one RC network. So you can name the resistors 5K, 5K, 5K. So this is RA, this is RB. Okay, now you can short this terminals. Right. Now important point is we have to put a comparator, right? You have to put the comparator. So where to put the comparator? We can put the comparator here, one comparator and another comparator here. So this I'll say the reason. Okay, so please try to put the comparator in between this resistor. So this is a non-inverting, this is a inverting, this is a non-inverting, this is a inverting. Okay, so the comparator terminals are connected to the flip-flops. This is R, S, Q, Q bar. So from here you take a one branch, second branch is a third branch. So from here you connect NPN transistor, mark the terminals. So here you connect on PNP transistor. So that's it. See, now this emitter terminal can be connected to the ground. So name the transistor Q1 and this is a reset. Then this will be Vref. So we can name the terminal collector, emitter, base. So this is a PNP transistor. So that's why the arrow is towards the base. So this is the NPN, it's towards away from the base. Now connection, like a upper comparator connection. See here, in the upper comparator you have a non-inverting and inverting. In the lower comparator you have a non-inverting, inverting. So in the upper comparator, inverting terminal, that is minus, should be connected to this divider network. From here 1/3 of your VCC will be going to the comparator for the comparison. Right, that is a biasing voltage towards the comparator. So this plus terminal will be connected to this RC network. You can see very clearly that is connected below the RB. Okay, in the lower comparator the plus was connected in the divider network. That is 1/3 of your VCC. Very important. And minus was connected to the RC network. So I said clearly the pin 6 and 2 are connected in the same RC network. Right, this is the 5th pin. Right, then this is your capacitor C and this is everything most over. Now see, very important part is not connected is the Q1 collector terminal. See here to be not connected, so I will just put U curve and connect. Where to be connected? See, you have to connect RB above. Okay, so you can encircle this transistor. So here you will be getting your output. So now we will see the working principle of Astable multivibrator. First I will explain you the basic scenario. Next I will explain the table. Okay. First, initially you consider this is a Q. Okay. So Q will be 0. Q bar will be 1. That means the Q bar is 1 means the transistor Q1 will be on. Right. If Q1 is on, it transistor in operational. That is, it is in on state. If transistor is on, we know that it is short circuited. Through which path? Through this path. See. So it will discharge. So through RB and C, it will discharge completely towards ground, 0. Now what is the current output voltage? 0. Okay, that is your output here. Okay, that is 0. Now I am giving a supply, right? So the capacitors keep on charging. Capacitors keep on charging. See, very important thing is the lower comparator, the plus terminal is connected to 1/3 of your VCC and the minus terminal is connected to 2/3 of your VCC. So here very important to insist again, the lower comparator or upper comparator. If you take any comparator, the comparator will check the 2 voltage. If the voltage in the plus terminal is higher, when you compare with the minus terminal, the comparator is going to the condition of logic 1. That is very important to understand here. So the capacitor is keep on charging. If the second terminal voltage is less than or very close to 1/3 VCC, right? That means if the capacitor voltage is less than this 1/3 of your VCC, that is in the plus terminal, right? That means you will be getting a logic of 1. Understand? Getting a logic of 1. So now what is the current capacitor voltage? 1/3 VCC. Precisely very less than 1/3 VCC. Okay. So now what happened? We will be getting logic of 1. So this will be 0. If set is 1, Q will be 1 and Q bar will be 0. So if I am giving 0 to this transistor Q1, what happened? This Q1 will become not operational. So what happened? If not operational means this will be disconnected. This path will be disconnected. This discharging path will be disconnected and it will be used to charge via which network? Through this RA and RBC network. Right? So it will become open circuit and it will used to charge. Okay? So now we know that when it was started 1/3 VCC used to charge through this network. The network is RA RB into C. To where it will charge, okay, it will keep on charging because here 6th pin was connected to the same terminal only, same node only. So when this voltage, capacitor voltage is greater than 2/3 VCC, immediately the upper comparator, previously it will on because the plus is connected to this RC network. Up to that this is used to charge through this lower comparator logic. So when it get 2/3 VCC, next state is going to change. So up to that, what is the output in the third terminal? During the charging period, the output will be high. Understand? During the charging, the output will be high. The logic of 1. Hope you clear. during the lower comparator period, the capacitor used to charge. Why? Because of lower comparator is 1, Q will be 1, Q bar will be 0, so the transistor become not operational, so it disconnected from the clamping network, so it is start to charge via RA and RB. So the next condition is when VCC is capacitor voltage is greater than 2 by 3 VCC. What happened? So immediately the Q1 will become operational, right? So when this capacitor voltage is greater than 2 by 3 VCC, we will be getting logic of 1, here we will be getting 0. So that means here we will be getting 0 and here getting 1. So if I am giving 1 to this Q1 transistor, Q1 will be operational, this will be discharge. Through which network? Through RB and C network. So before it was 1 by 3 to 2 by 3 VCC, right? Now it used to discharge. So this is a working this condition, that is when upper comparator is on, it will discharge up to 1 by 3rd of your VCC. So during this period lower comparator, during this period upper comparator. So the discharging is because of RB into C, the charging is because of RA into RB into C. Okay, this is the logic how your astable multivibrator is working. So I'll put in a simple way. Initially Q will be 0 and Q bar will be 1. So that means the transistor Q will be on, so it will discharge. Through which network? RB and C. That is very important. Right? Now consider your capacitor voltage is 1 by 3 VCC, very close. Okay, so it is capacitor voltage is less than your 1 by 3rd of your VCC. This is a voltage which is connected to the plus terminal of your comparator. Okay, the plus you consider like this, plus minus, it is connected to plus and minus is connected to this. Okay, that means what is the comparator output? Comparator output will be 1. So that means S is 1. Right, if S is 1, R will be 0, Q will be 1. We know that if set is 1, Q will be high, Q bar will be 0. If Q bar is 0, the transistor will become, Q1 will become off. So what happened is used to charge. It is unclamping, used to charge. Through which network? RA, RB and this capacitor network. So used to charge. Okay, then third period is, so capacitors keep on charging when it reach more than 2 by 3rd of your VCC. 2 by 3rd of your VCC. Immediately what happened? S will become 0 and R will become 1. If R reset is 1, we know that Q will be 0 and Q bar will be 1. So immediately your transistor Q1 will become on and this will discharge. Through which network? RB and C network. Okay, during this period your output will be 0. During this period the output will be 1. During this period output will be 0. So here the output, the capacitor output will be something like this. See, 1 by 3rd to 1 by 3rd is your starting voltage. Up to 2 by 3rd of your VCC, your lower comparator will work. When so this is 2 by 3rd of your VCC, right? When this capacitor voltage is greater than 2 by 3rd of your VCC, the upper comparator will on, it it will use to discharge. Okay, this is a part of your upper comparator, discharge through RB into C. Okay, so this is a way how your Astable is working. So I explained you in simple way. With this you can understand the logic clearly. Okay, so here I just given the explanation, you can read it. The timing resistor is split into two, RA and RB. I already explained. When VCC is connected, the capacitor is charged toward VCC with the time constant RA plus RB into C. Obviously you know. When the output pin is high. So what you want to understand is during the charging period, the output pin will be high. When it is high, Q bar will be 0 obviously. So very important, when it is charging, your output will be high. That time Q will be 0. That's what I explained here, right? That time it is an unclamped capacitor. So Q1 transistor is not operational. That's it. Very simple. When capacitor voltage is equal to 2/3 of your VCC, the flip-flop, the comparator trigger the control flip-flop and Q bar will change to 1. The Q bar will change to 1. Right? So transistor will go into the on condition. So capacitor will discharge. So when transistor on, the capacitor will be discharged through this RV network. This is very important to understand. Okay, so this is a logic, continuously it switch accordingly. Okay, so the upper lower comparator, upper comparator. So when it will work, when this second pin is have less than 1/3 of your VCC, this lower comparator will on, so it's keep on charging. When this capacitor voltage is going greater than 2/3 of your VCC, this upper comparator will on. So this is a period of discharging, this is a period of charging. Okay, the charging is nothing but a RA plus RB. During that time your output is 1. During the discharge happening through RB into C, that time you will be getting the logic of 0. So that is a logic of Astable multivibrator. So here we will go for the derivation, very important. So in the capacitor charge from VCC by 3 to 2 by VCC by 3 through RA plus RB, and discharge from 2 by 3 VCC by 3 to VCC by 3 through RB. So that's what I explained, right? The charging, because of this point, this is VCC by 3 to 2 VCC by 3. The discharging 2 VCC by 3 to 2 VCC by 3 through RB network. So this is what they're trying to explain in this slide. So this period is a on period and this period is a off period. This is a T on, this is a T off. We are going to measure now. So you can see here 1/3 of your VCC to 2/3 of your VCC is your on period. 2/3 of your VCC to 1/3 of your VCC is off period. The T on, T off. We are going to measure the what is the pulse duration. So this will repeat continuously. Okay, now we will see the derivation. Now we want to find what is the T high. So what we will do, first I will put the, okay, so this is your 0. I am taking this as a 1/3 of your VC threshold voltage. From here 0 to this point is 2/3 of your VCC. This I am taking as a T1. Okay, this period from here to here, this I am taking as a T2. Okay, now we will see the explanation. So the charging capacitor voltage V0 equal to VCC into 1 minus e power minus t by RC. So T1 is the time to charge from 0 to 2/3 VCC. So I am taking as a T1. I am customizing the equation VC T1 equal to what is the maximum voltage, 2/3 VCC. VCC into 1 minus e power minus t by RC. If you solve, you will be getting T1 equal to 1.09 RC. So VCC will get cancelled. So 2/3 minus 1. If you bring this one to this side. So you will be having minus E T1 by RC. Right, if you take LCM, what you have? You have minus 1 by 3 equal to minus e power T1 by RC. Take natural logarithm on both sides. So minus minus will get cancelled. If you take a logarithm of 1 by 3, so this exponential will get cancelled. So T1 by RC. So if you calculate for logarithm 1 by 3, you will be getting 1.09. So minus T1 by RC. This minus minus will get cancelled. So T1 equal to, I am rewriting, so 1.09 into RC. So that's what this is derived. So T1 equal to 1.09. So the T1 time period is 1.09 RC. Now we will go to the T2. When you see the T2, the maximum time period is VCC by 3. So I am putting VCC by 3, VCC into 1 minus e power T2. This period I am taking as a T2 by RC. So if you solve, what you will get? VCC will get cancelled. So 1 by 3 minus 1 minus e power T2 by RC. So you will be getting minus 2 by 3 T2 by RC. So this here T I am taking as a T2. So if you take a natural logarithm on both sides, this exponential will get cancelled, T2 by RC. So if you find this value, you will be getting 0 minus 0.405. So minus T2 by RC. This minus minus will get cancelled. So T2 equal to 0.405 into RC. So this is the time period for T2. Now question is, what is that on period? On period is from 1 by 3 VCC to 2 by 3 VCC. So this is the on period. So that means, so this is T1. If I subtract this period, you will get the T on period, right? Understand now? So T high will be T1 minus T2. So this is T1, this is T2. So this period minus this period will get this T high period. So we know that T1 is 1.09 minus 0.405, will be getting 0.69 RC. So this is on period. So we know that R is nothing but a RA plus RB. So it was written like 0.69 into RA plus RB into C. This is a on period. This is a T high period. Similarly, when you find for discharging period, so VC is a capacitor voltage, V initial is your starting of your discharging point, e power minus T by RC. So here you can see this is your 2 by 3 VCC. So it ended 1 by 3 VCC. So the capacitor ended. So this you should take it as a VC and this you should take as a V initial. So I am substituting the equation. So V initial I am substituting as 2 by VCC by 3. The capacitor voltage I am taking as a this VCC by 3. Okay, that is the end of your capacitor voltage. So you want to see only end of your voltage, that you should take it as a VC. So if you calculate for this, so again just cancel, and if you calculate this, so I am taking this at T low by RC. So you will be having 0.5 e power T low divided by RC. If you take a logarithm, natural logarithm, so e power T low by RC. So what happened? You will be getting 0.69 minus 0.69 minus T low by RC. So this will get cancelled. So T low equal to 0.69 into RC. So this is the time period for discharging period. So what you want to remember is T on is 0.69 RA plus RB into C. T off is 0.69 into RBC. Okay. See, the RC is a generalized one. The RB I have substituted, that is a network used for the discharging. So 0.69 RB into C. Now we want to find what is the total time period. So T on, T off. This is a T on, so T off. That is T. So T on plus T off equal T. So that is, if you add this both the equation, you get 0.69 into RA plus 2 RB into C. If you calculate the frequency, there is an inverse of time. So 1 by 0.69 into RA plus 2 RB into C. For simplicity, they have written 1.45 divided by RA plus 2 RB into C. That is 1, if you divide 1 divided by 0.69, you will be getting this 1.5. Okay. So next, if you want to find the time period, when suppose if you want to find the duty cycle of low, so what is the formula? T low divided by T into 100. So T low is nothing but a RB, because of this resistor, RB divided by RA plus 2 RB into 100. Suppose if you want to find the output goes high, so what is the formula? T on divided by T into 100. So in that way you can see the what is the duty cycle of on period and duty cycle of the off period. Okay, so these are the concluded point.